Hello, everyone. Welcome back to today's session of the Causality for AI and ML winter term. Today, I'm going to be giving the lecture, and the lecture is going to be about basics. So last week, we heard from Dave a lot about the motivation behind causality, the necessity, essentially. I gave some heads up on just course logistics. And today, we are going to cover the basics, the prerequisites, the background, which we're going to use for the actual conceptual new insights in this lecture. A brief overview. So we're going to have three main sections today. The first is going to cover probabilities. So we are trying to answer the question, why probabilities? So looking really at probability theory, the grounding, at examples. Then we are going to jump to a very important concept, independence, right? What is independence? What is dependence? And all the related topics, conditional independence, testing, and so on and so forth. And finally, we're going to look at graphs, the groundbreaking conceptual underpinning of Pearl's causality framework. And specifically, we are going to relate it to both probabilities and thereby also independence. Let's jump right into it. So section 1, why probabilities? So we have these law-like rules, but we are essentially unsure about being correct. But it comes with multiple reasons. And this whole lecture today is based mostly on existing textbooks. So Pearl's causality textbook. When it comes to probabilistic graphical models, also Koller and Friedman, and also the elements of causal inference by Peters et al. So Pearl essentially gives two reasons. And we're going to start with reason 1, coping with observations. And now we are going to switch to the live recording from last week. 3, 2, 1. So essentially, cases like this, for example, right, where the outcome is merely likely, right? So we usually say something like reckless driving causes accidents. So I was in a hurry right now. I was driving, hopefully not recklessly, right? But there was an increased risk of accidents. But also, you'll fail this course because of your laziness, right? Obviously not the people who are here, right? Because they've come here on a Friday. With shitty weather, so that's nice. And yeah, probability theory is a sound framework for essentially working with noisy observations, right? So it's a great formalism for doing things. And also recent research only looked into, grounding it properly in probability theory, which means that, we look at, the measure theoretic side of things, but this for another day. The second thing is, avoiding exceptions, right? So for example, if we have these two statements, right? So my neighbor's roof gets wet whenever I hose mine, right? Or if I hose my roof, it'll get wet. You could get to this wrong conclusion of, my neighbor's roof gets wet whenever I hose mine, right? Which doesn't make sense. So in a sense, also to cope with exceptions, we want to employ probabilities. Yeah, you're going to see a lot of these, right, from Russell Monroe, these XKCD comics, right, just to lighten it up a little bit and also have, this satire sketches here. So what we have here is number 2494, flawed data. So on the left, we see, we realize all our data is flawed. And now there's 3 responses of working with this, right? So, we could say we are not sure about our conclusions. This is similar to the motivation you saw last week, right, with the biology data, where we essentially said, okay, the best thing we can do is I don't know, if we don't want to talk causality. But then, we can also say something like this, which I don't want to piss on anyone's foot, but happens a lot in research nowadays. Yeah, so and then yeah, well, because we're in an AI class, right? So we train AI to generate better data. With all the craze around ChatGPT and similar models, it's exciting, but it's also, you got to be cautious. So I wouldn't necessarily say very bad, right? But it's yeah.
So what if we use the causal model to generate our data?
Then it's awesome, yeah? See? Because it's a causal model, right? But then you're already talking about the important topics, right? So
yeah, then I know already why should I learn.
Yeah, exactly. Yeah, so we're going to do some formalities today as well, right? So just, introducing notations and things you're going to encounter a lot of times. I guess this kind of formalism you will only encounter in more foundational works, right? Really, because you're digging into what it really means when we're talking about random variables and all these kinds of things. So we cover them so that you see them. Well, essentially, probability theory is based on a model of random experiments or a probability space, right? It consists of, it's a tuple of these different objects here. And I've denoted here what these objects mean. So omega, big omega is a set containing all kinds of possible outcomes. in a minute, we are going to do an example to understand more what this really means. F is a collection of events, A, right? So A, B, C, all these kinds of different events, which are subsets, so potentially even equal to omega. And P, the P that you usually denote the probability with, is actually a measure. It's assigning a probability to each event, right? It's a special case of measure theory where we have certain conditions, like, for example, that probability can never exceed 1 and so on and so forth. A random variable then, here denoted by X, is actually a measurable function. So it's actually a function, right? It's the thing which, does the experiment in sense. From a probability space to a measurable space, which is here now denoted by this two different H, this calligraphic H and the regular H, where the regular H is just a set and this calligraphic one is a sigma algebra, right? Don't worry about all of these terms, right? You can always look them up, right? We are going to do an example now. But essentially what it's just telling you, it's going from all of these possible outcomes to this specific set, whatever that is, right? And you're going to see in a moment. So famous example, some of you might have had this in high school as well. So a coin toss, right? So we have our random variable X and now represent the outcome of a fair coin toss. Omega in this case would represent all the ways that you can actually flip a coin, right? Like there's infinite ways, right? How the dynamics will shift it when it, goes up in the air, how long is it in the air, when it falls, where it falls, and so on and so forth, right? And then F represents an arbitrary collection of such tosses, actually. So what is H then? H would just be the result, our encoding, so heads or tails, right? And naturally, we can just represent it as something binary. For example, heads being 0 and tails 1. And then this calligraphic H is the group of the outcomes, right? It's a set of sets, essentially, right? So, they could be the empty set, they could be the full set, right? And then there can be these in-between outcomes where we just observe, the coins landing as heads or tail, right? And there's infinite ways of how it just could end as either heads or tails, right? But that's what you do here, right? You want to have this mapping that all these different ways I can do my experiment that actually leads to something I specify. In this case, it makes sense for a coin to specify it like this. And yeah, for example, if we look at then the probability of the coin being, heads, so X equal to 0, then actually formally, right? So what you will know is this one here, Px equals 0, but formally what you write is this rather complicated term, but let's break it down, right? So P is again the measure, the probability measure, X is the random variable, and to the power of -1. So we are inverting it, and we are looking at an omega, and we're looking at all these omegas where actually X would be 0, right? Like all the ways the coin could flip and then land so that we evaluate it as heads. And because, it would be tedious to write this down, especially if you introduce conditions and multiple variables and interventions, we just opt for this simplistic notation. And yeah, of course, for a fair coin toss, this probability would typically be 0.5, right? So 50% of the times we would expect it asymptotically to be heads or tails. It's a Bayesian formalism, right? So that's actually the formalism that Udapol looks at. Specifically, the Turing Award we talked about last time that he got was, well, for causality, but he pioneered these Bayesian networks, right? And the name is already implied. And these axioms are essentially the following, right? So there's the boundedness property. So, we are between 0 and 1, right? For any of the events from the set of possible outcomes. Then there's the sure proposition, right? This was what we just saw earlier, the set where all outcomes are in there, 0 and 1 for the coin toss. This must be 1. And then also this property of being mutually exclusive, right? So if I have two events, right, then if they are mutually exclusive events, so they're disjoint sets, then it's actually a sum. Then we can just decompose this probability of this event happening, so either A or B, as just A and B separately and sum together. Now, looking at one important quantity or one important operation is marginalization. So essentially, the law of total probability, as it's known, states the following: that if you have an event, the probability of an event A, that essentially you can look at a joint probability with other events, disjoint events BI, denoted here, right? I is just an index suggesting there's multiple of these B events. And marginalizing now over B gives you this PA. So we are summing over all these terms, right, and collecting it together. So we are, in a sense, averaging, in a sense, over this information on B. Just an example here as well. So, for example, if A is a random variable which now looks at dice, right, rolling a dice, and it's the outcome of two dice being equal, right? So you throw two dice and you look at the number which comes out. You want to determine if they're equal. And B is the random variable which now denotes the result of the first die, right? And now using this marginalization operation, what we can actually do is compute the following, right? So we can actually look at, what is the probability of two dice being equal? It's 1/36, right? And because we have to do it 6 times, we end up with 1/6. Now, another important property, which now relates to the marginal probability, is the conditional probability, right? So we start off by looking at the joint probability, so probability of 2 events essentially just, yeah? And this probability is just being read as both events happening, like if we take the example from before, right? Outcome of the first die being some number, and then the property also whether it's equal, both things happening essentially in the same experiment. What's the probability of that? And using that now, through the marginal, we can actually get the conditional. So you see, here we have this just defined joint probability. Here we have the just discussed marginal probability. And now what we can get is this conditional probability. So, given B, what does it tell us about A? What is our belief about A? And this is really the intuition, which you're going to encounter a lot. Famous Bayes rule, right? So it's a Bayesian formalism, and Thomas Bayes had this rule, right? It follows really from all of these laws and fundamental concepts, but I chose to present it in the following, as such that essentially it's a consequence of both of this symmetry essentially in conditional distributions, right? So we just saw the A given B, but now we can also do the same thing for B given A, right? As you can see, it commutes whether we write AB or BA, doesn't matter. So I just write AB to indicate it's the same object, but just the denominator is changing to PA, and then you get the reverse, right? Like, what if I knew, the outcome of the 2 dice is equal? What does it tell me about, the first outcome? And essentially what this gives you is the Bayes rule, right? So it maybe from machine learning classes, right? Like if I have my prior A, and then I have my likelihood about, for my data, then now I can, judge about my hypothesis given the evidence, right? Given the B. And this is really the decomposition we see here above, right? Just placed in and replaced. Yeah. And so this is kind of the key idea, right? That, A can be interpreted as our hypothesis and B as our evidence, right? Like in the light of new data which comes in, we can update our beliefs opposed to, frequentist view. But there's a whole other discussion. This is just for the basics for what we need in causality. Yeah, so here another comic. Given these prevalences, is it likely that the test result is a false positive? Well, it's a lecture on Bayes' theorem after all, so yes. And yeah, sometimes if you understand Bayes' theorem well enough, you don't need it. So I think what's really cool about this specific sketch is that, as I put on the previous slides, right, when you have some intuition, that essentially you can just work with that intuition, right? Like if you're doing foundational work, you need to get into the nitty-gritty, I guess. But oftentimes you can just, juggle with these concepts. Now, another important property, as you can see, this is like a big overview of a lot of these concepts which you might or might have not encountered, or at least, in some kind of way. And another important aspect is chain rule, just like in machine learning, chain rule is important, for backprop and these kind of things. In general, it's an important concept when we have a set of n events, right? Here denoted now by E, for event. And essentially, we just have this decomposition, right? So, we take this last argument, for instance, and condition on all the previous arguments. And then we take the penultimate argument and condition on the previous before that, and so on and so forth. We imply an ordering and end up with a prior over, for example, the first event. Now, what is really statistics? So the way I see it, at least for the context of this lecture, is that it's kind of the inverse problem, right? So in probability theory, we looked at probabilities and these kind of things, and densities, and now we are looking at, we are having data, actually, we're having the observations which were implied by those and want to go the reverse direction, right? So we want to learn from the outcomes of the experiments about the objects we just discussed, right? Like marginal, joint, conditional, and so on and so forth. And typically what we have is data points, right? So for example, for 2 random variables, X and Y, and then we have a set of n of those data points, observations. And now we ultimately want to learn, for example, this generating distribution pxy. Here, x is in some kind of space x and y in some kind of space y, and typically we call those inputs and outputs. And there's many different ways, right? Like, in statistics, we might call them covariates, right? Machine learning, we might call them features. And for the outputs, the same, targets, labels, whatever the context is. And typically what we assume is that they are independent and identically distributed, right? So identically distributed, of course, because, well, we assume they are all coming from the same data generating process, right? The PXY. Independent, because what you're saying is really like that, I run this one experiment and now it should not give me any information, leak any information about any of the other independent runs of these experiments. Another important concept is that of expectation or expected value. So if, again, we have a random variable x, and this time it's actually real valued, so you see that the space is chosen as the real numbers, then the expected value, or sometimes also called mean, is given by this formula. So this is just a notation. We just write e of x, right? And what it really means is, in this case, for the categorical, without loss of generality, we can define this in terms of densities for continuous variables, is, well, just an average, essentially, over all the different values x can attain, but weighted using their respective probability according to our random variable. And you can actually generalize this. And I think this is a nice way of seeing it because it connects the different families we're going to see now. Essentially, if you just put a function g over this x, then you just replace the term x here with a gx. And now you can play with g. You can change g. And for example, if you change g to be the following function, so just a random variable minus its expectations squared, then you get what we know as variance, right? Typically denoted by, the sigma squared. Now, what is really correlation, right? So Dave told you last time about, correlation, causation does not imply it, and so on and so forth. Well, correlation is just derived from covariance, right? So if we have a pair xy, then, if we have this function now gxy, again, right, like you can just extend this to sets, then we are looking at the following. So it's a product of a similar structure, right? It's not a square now because we're not doing it for the same variable, but between two variables. But essentially, it's the same then as variance, which, implies the name covariance. And then you can actually define something like the Pearson correlation coefficient, typically just called correlation, as following, right? So you just take this covariance and you scale it. And you scale it by essentially the standard deviations, right? Like the roots of the variances. And, when this rho xy, that's the typical notation for correlation, is 0, then we say it's uncorrelated. And obviously, if it's non-zero, then we say it's correlated. And yeah, so here's one on correlation. So I used to think correlation implied causation. Then I took a statistics test, now I don't. Sounds like the class help. Well, maybe. Okay, so this was on probabilities. Any questions or thoughts, impressions, really, right? Like, we should keep this open, right? And don't be shy. Also not because Christian is here, right? Christian is really cool, yeah? Yeah. So Kolmogorov, as far as I'm concerned, is talking about algorithmic information, right? Or algorithmic, processing. So you can relate statistical independence and algorithmic independence, for instance, right? Do you have anything specific in mind when you talk about Kolmogorov axioms?
I just want the slide about the data axioms. Can I go back?
Sure.
Isn't that like getting the condition of the Kolmogorov status? Yes.
I would have to check. But maybe you can show me also in a break or after the class. Yeah, but interesting. Okay. Yeah. In general, that's when you also encounter Kolmogorov complexity and these concepts in causality, then it's really just an alternate notion to what you usually do in probabilities, right? But obviously there's a relation. There's like an analog, right? But it's
So some people call that.
Some people just call this thing. Okay.
Okay.
Oh, sure. I mean, whatever you want to call it. I don't care. Yeah.
It's like about the base rule and conditional probability referred to be as evidence. I wanted to know because
I also have the concept of evidence in my head as a likelihood-related concept, like from evidential neural networks and stuff.
Yeah, I mean, if you think about it, right, like in the likelihood term, you also have the B, right? It's just if you think about it, right, like what you're saying here, B is evidence, A is hypothesis. So what is the probability of my hypothesis being true given my evidence, right? And here it's the reverse term, right? Like the probability of my evidence given that I assume the hypothesis to be true, right? And that's the likelihood, right? Then let's maybe keep moving. So yeah, section 2. So now we have, motivated probabilities, right? We have seen these two reasons and we have discussed how they are essentially formalized, right? Looked at some examples, some comics, and now what is independence, right? So, what information do variables share and how to test for it essentially, right? Like independence testing as well. It's an important topic in causality, which I feel like is oftentimes left out actually because, people want to talk about foundational ideas, but not how to implement it. So yeah, probabilistic independence, we define it as following, yeah? So we are really just equating these two quantities that we have seen earlier now, yeah? So if we have px given y times py, which is just the joint xy, and decompose it now the other way around, if all of that is just equal to the factors, right? Like just multiplying the marginals, then this is what we call independence, right? And the typical notation we are going to use here is just this kind of perpendicular thing here with the p denoting that's in distribution. And the intuition here is really that, knowing x or knowing y, for that matter, won't help you with y or x respectively. Factorization. So if we remember for a moment this chain rule we just saw, right? So with a set of n events e, then essentially that's what we call a factorization, right? Because we end up with all of these factors multiplying together. It's a big product essentially, to just get this bigger set of joint probabilities. Interestingly, right? So mutually independent implies pairwise independence, but not the other way around, right? So if you have this property, and now you look at any pair EI, EJ, then they will actually be independent. But if you have those for all the pairs, that doesn't imply that they are still mutually, jointly independent. Now, conditional independence, this will be a very important topic, so I'll try to stress this. So if we consider a triplet of sets now, x, y, and z, then the first two are conditionally independent. That's what we say, given the third, if and only if the following holds true, right? There's different ways of writing this down. I'm choosing this specifically because it's going to help us with everything else in context. But essentially, if we look at the joint given z, right? Like I've observed z, and now I'm trying to look at the joint probability xy. If that just factorizes to x and y, given z separately, for all of the instances, x, y, z can take, where most importantly, z can actually occur, then that's conditional independence, right? So really, this is just a sanity check, right? So essentially, it just tells you that, if an event cannot occur, right, and you have this property, it doesn't mean anything, yeah? So an event has to be able to occur, and then for all of such events, we want to have this property, right? Because then really there's no information going from x to y or vice versa. Now, this is maybe likely something very new, right? So there are these special rules. These are now coupled already to what Pearl did. Actually, Pearl, I think, introduced those in the 80s or 90s in the context of graphoids and similar things. We are going to encounter them in a different context also eventually in the lecture. But really, it's just a question of independence, right? And properties of independence and therefore probability theory. So essentially, the following three rules. Symmetry. This kind of makes sense. By the way, when I drop the P subscript here, right? So then, if it's obvious, then I'll just drop the subscript. If we need differentiation, I'll have it in there. But yeah, x being independent of y given z, well, it's the same as y being independent of x given z, right? So it commutes, doesn't matter how we write it down. Good thing, easy thing. Then decomposition, that's a bit more interesting already. So if we have, a joint set essentially, so there's some partition, right? Like we have the set YW, and it's partitioned into Y and W. You could just call this another set C, for instance, right? But it decomposes into Y and W. Then what this implies is that you can just take away variables, right? Like you can take away this W and just look at Y, and the independence still holds. So just by adding things, it won't break. And then there's this weak union. Looks maybe a little bit more complicated already, which is essentially the same game as before. So we have this partition, we have these extra variables W. But now what you can also do is just push them back into the conditions. So this also won't matter for the conditional independence. It's not important to understand them right now. We are not going to play them through. It's more of an overview to show you these things and what they mean on an intuitive level, at least at first. Then there's also two, yes?
Is there any reason why X and Y is switch places in between, and was it just symmetry again?
You caught me here doing something wrong when I was typing the PowerPoint. I was just flipping it. But as you correctly stated, you were already inferring the correct thing. Because of symmetry, it doesn't matter. So it was a test, actually. See, so many smart people here, really. Okay, so Causality, come in, please. No, yeah, that's what Yuda would say. Okay, so contraction or an intersection, these are two even more peculiar and special rules, right? So there you have as only rules two conditions before we have the implication. First of all, which is x being independent of some z, and then further, x being independent of what we previously called these extra variables w, when there's y in the conditioning set. And when you have both of these properties, then what you can actually do is just pull the w into the set with the y. So this is kind of the reverse direction now. If we just remember, here we kind of remove the w, and now if we have these two conditions, we can actually just bring it back in. Yeah? And that's very important because, you know, if you're trying to do some proofs, some, you know, equational algebraic proofs, then you need to be able to go in both directions oftentimes. And then intersection, it's the same setup, at least here. Here it's just slightly different. So you have w now being in this set here, in this conditioning set. Then you can actually also do the same thing, right? So whether w is in there or not, doesn't matter. Yeah? Understanding the intuition behind the naming and so on, it's a bit more involved. It's not so important here right now. Now, the first connection between correlation and independence, right? Or at least the first topic we're going to discuss. So, you know, when x and y are independent, and now we are talking marginally, so there's no conditioning set, then we actually have that they are uncorrelated, yeah? But it's generally not the other way around, right? So if we see a correlation of 0, doesn't mean they're independent, yeah? And this is a simple example. Of course, there's special cases, right? Some Gaussian case and so on, where this is the case, yeah? But in general, it's not the case. And this counterexample shows why. So this is just some R code. You can also run this. There's online modules to running R code. I mean, I guess in our research, we mostly use Python, and a lot of people are probably also used to Python here. But there's a lot of R in Causality because obviously the close connection to statistics and you know, potential outcomes, people, I'd say they mostly use R. So this is just loading a library. Then we're just setting a seed. So, you know, this is reproducible. So you could just use this and get the same numbers. We have two variables now, two noise variables, yeah, A and B, we call them in this case. Yeah, they are just a random uniform distribution shifted by 0.5, and we just take 200 samples. That's what it means here. And then we have X and Y. This looks a little bit more complicated, but the T and C, so T stands for transpose and C is concatenate. So it's a bit obscure. I like Python more because it just tells you what it means. You don't have to remember. But really, the only mathematical functions here are the cosinus and sinus. And this weird little thing is the add in PyTorch and so on. So it's just a matrix multiplication. And R bind is again a type of concatenation. So what's happening here is essentially that X depends on both A and B, and Y as well, right? But just in a bit different way, right? So cosine and sine, the negative sign of P fourth, and the other way around. And now what we do in this last two lines is we first check correlation, you know, this Pearson correlation coefficient, and then we do, so we are going to see what this DHSIC means, but it's a way of testing independence. And what you can see here now are the p-values, right? And the null hypothesis. We are going to explore all of these and what this means again in a moment. But just briefly, what this really just tells you is that they are uncorrelated, but they are dependent, right? And this is exactly what we just wanted to show. And this is an example of showing this. So dependence implies correlation, uncorrelatedness. Independence implies uncorrelatedness, but not the other way around. Now we are also going to look at, partial correlation, conditional, and so on and so forth. So if we now introduce like a conditioning set, right? We just saw X and Y, but now we also have a Z. Then this generally doesn't even imply that the correlation, the partial correlation coefficient will be 0. Yeah, it's not important even how you compute this for the moment, right? But it's just worth remembering this fact. Just like in mathematics, sometimes when you do some proofs, it's just good knowing some things. An example to show this. So similar to how we just did now with A, B, X, and Y, we're going to do with 3 variables, Z, X, and Y. So these n ones are noise terms, right? And we just write a subscript to indicate to which variable. It could be called 1, 2, 3 or other symbols. So we have 3 noise variables, X, Y, Z, and we have this independent statement here. And Z is just that noise. X is Z plus that noise. So essentially it's NZ plus NX. And then Y is Z plus NY, right? Again, similar structure as before. And importantly also, NX and Y are uncorrelated but not independent. So, and essentially you can by this example you can already prove this and even the other direction, right? That it's not implying independence, which was anyhow not the case even before that, before conditioning. Yeah.
Is really an X and then Y uncorrelated, or is it rather X and Y? Because an X and Y are this.
So you have just NX and NY uncorrelated but not independent as a condition, right? But then what you get is this thing here on X and Y, right? But for example, the partial correlation, like if you look into it, obviously it's going to be tied to NX and NY because it's defined over those, right? But that's how you calculate it and show this result essentially. If you're interested, we can discuss after the class, in more detail. I can show you also where the references and everything. Now, so we hinted already 2 slides prior to this. Hypothesis testing, very important concept. I always found it confusing, but then, preparing a lecture like this gets you again in the groove. Yeah? And essentially, it's not that troublesome, really, right? So if we think in practice now, right, like, or even in this theoretical framework, we are concerned with uncertainty, right? We got to get somehow comfortable with, the fact that we are not going to know everything, or not everything is always going to be perfect and exact, right? And that's exactly the intuition here, right? So any independence measure or probability space, it's not going to be exactly 0, right? Like if you're measuring, for example, correlation, yeah? And so we need to take into account the randomness inherent in our data sample, right? Like what kind of sample I observe, how big is the sample, and so on and so forth. And so essentially we are looking at what we call these test statistics. So it's just a function T over our data sample D. And really what is happening is that this H0, which we are going to call our null hypothesis, we will take that and accept that essentially if our test statistic is smaller or equal to some kind of threshold, right? And these things are related to things we choose as users, so significance level and so on, to control what they call type 1 and type 2 error. But more on that in a minute. And in the other case, right, you can see also this is exhaustive on the real line here now. We just take the alternative hypothesis, HA, right? So these H's are our hypothesis, so some kind of beliefs we have about our data, about some kind of relations in our data, for example, X and Y being correlated. And then depending on what kind of statistic we choose and how, we specify the parameters, we have a sure way of deciding, which again, doesn't mean it's the truth, right? Like it's just the way we set it, right? But if we do a good job, it'll tell us about some of the underlying truth of the world. Yeah? And again, here's an example, right? So null hypothesis could be something like X and Y being independent. And then the alternative, I just wrote H1 now here because of the 0, but whether you use A or so, doesn't really matter. Or the alternative could just be, well, if they are not independent, they surely should be dependent, right? So yeah, I really want to stress this point. So we really must learn to embrace uncertainty, right? So probability is not equal to a proof, yeah? even though, you know, probability theory and so on has been nicely formalized over the last decades. I think a nice story. So also what Christian always does with us, he always talks about CERN and CERN for AI and these kind of things. And at CERN, right, like with the huge collider and all these amazing experimental physics stuff going on there, they obviously also have noisy observations, right? They measure these things, right? And they look at these p-values as we have seen in our small example, just that, you know, at a much bigger and more complex scale. Yeah? But they look at these, what they call, you know, 3 sigma p-values, right? And they had one result rather recently where they thought they found a new force of nature, right? But they were cautious to say might, right? They were really, you know, in line with the spirit that it's not a proof, but it's a likelihood in a sense, yeah, a chance. And why? Well, because they got burnt before, right? So in 2011, they actually had a 3 sigma result, which is a significant result, right? But ultimately, they found out it was due to a faulty cable, right? And so really, they started switching to these 5 sigma. And again, it's also not a safeguard, right? But it's doing a little bit better than the 3 sigma, huh? So this I really want to drive home on an intuitive level and just what we take from there, right? Like not jumping to conclusions. It's a bit in line to the first XKCD comic we saw, right? That sometimes it's also good to say, I don't know. Yeah. Now, we just talked about p-value. We already saw an implementation. Now let's actually look at the definition, right? We are prepared for this now. So really just, it's the probability, you know, of rejecting our null hypothesis, right? And rejecting null hypothesis is just, you know, remember the case. It's just when our test statistic is greater than this threshold C. And if this quantity is smaller or equal to some, again, user set level alpha, right, which we usually call the significance level, then, you know, we want to accept, or we at least don't want to reject our null hypothesis. And the p-value is really just the smallest such level that we can get. Yeah? So if we saw the 3 sigma p-value or something, right, it's like really, really small numbers, right, close to 0. I mean, again, what is really close, but, you know, in the intuitive sense, layman term sense. So really, right, just for you to remember, right, without having to dive deep into it, right, if my p-value is large, then our data is essentially consistent with the null hypothesis. And if p-value is small, then our data is inconsistent with the null hypothesis, right? But in this nature of, you know, trying to find evidence against something, there's an inherent asymmetry, right? So essentially, when, you know, the p-value is small, then we are saying, oh, this cannot be. So that's why we reject and accept the other thing. But if it's large, then it's consistent, you know? And now maybe many of you would think, oh, then we should maybe, you know, accept this null hypothesis. But hey, it could just be that you didn't have enough data, right? Like that you didn't get enough signal, right? And so that's important to remember. So there's an inherent asymmetry as well in hypothesis testing.
Right, or if you don't get the right probability distribution. You make the assumption now, right? So you say this Gaussian, that even Gaussianity testing, whether your data is following a Gaussian distribution, is super hard if you go for big data. For example, there might be just one cable, and you just walk along, and you get one value different in a trillion of, you're not Gaussian anymore. So there are many other assumptions.
Yeah.
And so many statisticians actually say p-value, yeah, I don't know.
Yeah. No, I think also just, you know, Dave would now say, like, there's very smart people also at CERN, right? And so if they are cautious, then, you know, we should also be cautious.
Yeah, but that's the same argument as Stuart Russell is smart, and he's saying the world is taken down by AI, we should.
I agree.
No, I mean, proof by reputation, we should reject all of them, no matter what people do.
I'll tell that Dave. I was talking as Dave. No. Yeah, no, I agree. I agree definitely. Also, like things that we didn't just specify now, right? But if you look back at, for example, this thing here now, yeah, this is exhaustive, right? And even these kind of things. What if it's not exhaustive, right? Like, what if you look at whether the number is 0 or non-zero but greater than 0, right? Like you completely discard the negative space, for example, right? Or say you work with complex numbers or whatever it is, right? And then yeah, if it's non-exhaustive, then suddenly you can actually bias your result in hypothesis testing.
But then you can make it simpler. So imagine that you just have count data. So something that cannot be negative. most of the statistics tests fail.
Yeah.
I mean, and you don't know what to do.
Yeah.
And it's unsolved.
Should we call here the people to solve it, or how do we do it?
Yeah, sure. But we do that implicitly.
Implicitly.
Like the challenge and then tomorrow they.
Yeah.
So you should draw it on a blackboard. Tomorrow they release it.
What was the movie? Was it Good Will Hunting?
Yeah.
Yeah. No, oh, Beautiful Mind? Or what's it?
So Good Will Hunting had this.
Good Will Hunting. Yeah.
Beautiful Mind holding everything too.
Yeah. Nice movies. Okay. Yeah, so again to the drawing conclusions aspect of it, right? Just to drive this point home. So, we are typically collecting evidence against the null hypothesis. And as Christian was saying, really, right, like the p-value, again, is also not the ultimate thing, right? Confidence intervals, there's this whole area of calibration, conformal prediction, these things, right? Like they're all trying to get more certainty out of something which is inherently uncertain, right? But in style, it's really similar to a proof by contradiction somewhat, right? So you essentially assume the null hypothesis to be true, and then you look at whether, the data would make sense or not. Yeah, this latter point we already said, right? So if the p-value is small, then typically reject and accept the other one. And here another example. So this is really just the code example from before, just extended a little bit. So all of the parts are same, except for here we are using 400 samples now. And now we have two sets of variables x, y. So we have x, y, 1 respectively, and 2. And the 2 is the one from before, but just with 400 samples, and 1 is the one which just uses the original 200 samples. Yeah? We made sure to put it like this so that we have the same numbers as before. And now, if you look at the dependence, right? So again, we get the independence, but we get the dependence, but uncorrelated. But now, oh wait, did we? What was it again? Yeah, exactly. So again, right, we get the same result, essentially saying that they're uncorrelated. We don't have enough data to reject the null hypothesis of them being uncorrelated. But of course, we said, we should be collecting more data and so on. And if we do so now, right, we look at those where we have double the data, the value increases, right? It's even more consistent than before. And so we are even more sure, given this trend in the sense that, well, they should be uncorrelated, right? In this case, we know analytically as well, but this is just an empirical example also showing you that, these trends can also inform you, right? So to summarize, right, x and y independent, but our p-value says otherwise. That's the null hypothesis. So, we reject and take the other ones. So they are dependent. And in the correlation test, they are uncorrelated. In the null hypothesis, p-value is consistent. So we should collect more data. It's still consistent. It's even more consistent. And so we are justified to believe that it's rejecting H0 is likely correct. And yeah, here also the talk, for example, about exhaustiveness and all these other design choices. We essentially conclude always the alternative, right? Like if this was not exhaustive, also you would have to consider other options as well. Yeah, in a nutshell, this is something I found on the social platform Quora, right? Someone was asking, and then someone was giving this answer. I think it was funny. Yeah? It's essentially the question of belief in God and religion. I don't want to jump into this, right? But it's the analogy of fairies, right? That, for example, say I make, the claim that there are invisible and indetectable, importantly, fairies all over the place. Yeah? They're here everywhere. Yeah. And I'm actually saying that now. Yeah. And then because I've defined them as being indetectable, you can't possibly find evidence, of course, right? Because by construction now, I'm just playing this dumb argument, but sure. But should you now conclude that they don't exist or do exist for that matter? Well, no, of course not, right? And you have good reason not to. Anyway, slope hypothesis testing, there's also XKCD on them. So surprisingly, there's a lot less on like matrices and geometry and so on, but at least on probabilities, Russell has a lot. And what you can see here is, there's on the x-axis we have, students screaming and measuring the loudness in decibels. And then on the y-axis, you have the stats exam grade, right? So you see, for example, student A is both bad at writing exams and screaming. Yeah. Student C is somewhat better at screaming, and student B is somewhat better at exams. Yeah. And well, data is not significant, right? Like they measure, there's this positive correlation, but the p-value here, consistent with the null hypothesis. So yeah, we need more data, blah, blah, blah. And what they are doing is, well, they just have these students. They don't have actually more students, right? So what they do is each student just, screams a little more, yeah? And, they measure and suddenly they have the spectrum, right? Like, and of course it makes sense somehow, right? Like the performance didn't change because they didn't retake the exam, but, just the scream. But now the number game changed, right? Now you can see actually it's a significant result. And this also plays nicely in what Christian was just saying now, yeah? So, the person would here say, now, perfect, my job is done, yeah? And the other one is really just questioning, did I do the correct thing, yeah? Okay, now just briefly, so I told you that I'm going to tell you about this DHSIC, the HS stands for Hilbert-Schmidt, after the famous mathematicians, and IC is just independence criterion. The D stands for the multidimensionality, so D as in variables. And really, we don't have to understand this much, but this is some work going back to Bernard Schirkow and others with kernels and so on and so forth. So you have this kernel mu, and it operates on probability distributions actually, right? So on those P's directly, right? And if the difference between the joint and the marginals, which you can obviously get from the joints, in the norm of some reproducing kernel Hilbert space. You don't have to understand this for now, but it's a space with a lot of nice properties. If the square norm of this thing is equal to 0, then actually they're independent, right? It's a nice analytical characterization, right? And I think there was this original paper in NeurIPS also a while back from Arthur Gretton, and they looked at different design choices essentially for making this work empirically in practice, right? Because this at first is just talking about the actual distributions, right? If everything's perfect. But now again, we just have data. We have to estimate these P. We have to choose some kind of mu and so on and so forth. But this is the one we just used here, right? In this example from here, this library. I think originally from Fista and others, and yeah, works quite well.
So intuitively, it's measuring the mutual information on conflict, right?
Yeah, yeah,
looking at
exactly.
Approximately the joint if they were
Yeah.
And now they passed it as a regression.
Yes. Yeah. Also, just briefly, because we don't talk much usually about conditional independence testing. We just skip the nitty-gritty details. But somehow people say it's hard in itself. Well, because of all the problems we just saw, right, with probabilities and the nature of things, right? But then also just the difficulty even computationally, right? So consider just binary conditions, right? Like this could be also in the domain high dimensional and unstructured, right? But just these D variables with binary conditions, then really what we said earlier when we said like independent given Z, that actually for every instantiation of all those sets, right? Like this could be really big, right? Then in binary, of course, this would be just this exponential here. Then this needs to be satisfied, right? And so we have this exponential growth even of tests in the number of variables that we consider for the conditioning set, right? Imagine this is like a social network, right? Like it's horrible, right? Like, and you are not interested typically in just measuring, whether someone is friends with someone or not, right? You want to know all kinds of properties. Yeah, so this was on independence now. Before we move on to graphs, yeah, as before, any questions or thoughts or impressions, or how do you feel about CERN? How do you feel about these things? Yeah. Don't be shy, yeah. We're really, it's just us. Good. Then I keep moving. This is essentially, so yeah, I think we are quite good in time. So the final section of this session today, and it's going to be about graphs, right? Graphs and causality everywhere. You see them on the slides. I use them in the design everywhere, right? Like all of these are graphs, yeah. And yeah, it's a graphical notion after all, right? Like actually also like people are getting separated in the causality field, right? There's like these potential outcome people, and then there's the graphical models people, right? And we are the graphical models people now. So and what we're going to talk specifically about is not just graphs itself, but how they really capture relations and how we relate to everything we've just had before, probabilities, independence, and so on. So again, just briefly notation as we have had before with probabilities. So here we have a graph, yeah. So there's nodes, these things which have a name typically, Then there's edges between nodes, denoting some kind of relationship. And what we have are certain, you know, special sets, yeah, that have a name. For example, you know, here we have, you know, two arrows pointing into Z. We typically call those the parents, right? I don't know, Christian, where does these maternal and all of these family-related terms come from?
Statistics, they look a lot at biology
Hmm.
and genetics. That's where it's coming from. And
Okay.
back in the days where they had different moral ideas still, so that's why they're even then talking about moral links, and they're talking about how many parents we should have.
So, also immorality, right? Like it's always funny because it's essentially, you know, parents, but that they are not connected with each other. It's just a restriction. So yeah, I don't know. I'm not justifying any of those names. I'm just telling you why, you know, we're choosing them that way. For example, naturally, we would say something like Z is also, you know, a child of Y if we look from the perspective of the parent, essentially. There's other interesting sets, for example, a descendant, right? So for example, W is a descendant of X, right? Because somewhere down the lineage of parents or childs, there's a W. And then you can reverse the same thing, right? So Y is the ancestor of W. And then you can even talk about something like non-descendants, right? Like that's then more algebraic, right? Or set theoretic, right? You're just saying, yeah, it's not the descendants, right? Like you take the whole set, take out the descendants, and that's the set, right? Very importantly, I want to just mention, right? And this is just, you know, algebraic play now. But for a lot of notions to come, it's important to know that, you know, the variable is oftentimes also itself included, right? So for example, X is actually its own child, or, you know, the ancestors W. I mean, you can define those differently, but typically. And then, you know, for example, ancestor of W contains, you know, W itself, or the parents of Z and W together, you know, also contain those two. Okay. Oh, yeah. Mm-hmm.
And within the lecture, could you assume that the child contains either node against itself?
So I'd say the following. If you know, when do you need it? You'll probably need it only if you want to go through an example. And then in the example, either you need it or you don't. So you answer your question yourself, right? But you can just, you know the fact. It's just important to know, because then you can play with it, right? And if you really don't know, you can just ask me and we can look at it together. Yeah.
The example only hold true in a cyclic graph, right?
Which one?
The example would only hold true in a cyclic graph where, like, for example, W is again connected to Y. Was that, is this example true for this graph?
Oh, you mean, for example, this one here? No, this is just notational thing. In this case, it's true for this graph, right? Yeah. But of course, you could also write more naturally. If you say like it's a child of its own, you would feel like there should be an edge even from X to X, right? And that's why you said cyclic graph. Yeah.
So making the assumption that every node has its own ancestor or something doesn't add. So is it also that it's its own? So it's when it's its own parent, we assume reflexivity as in our relation.
When you say reflexivity, what do you mean?
That's the relation that builds the edges. It means that X is related to the same.
Oh, okay. Mm-hmm.
So that there's a connection.
And your question is what now? I mean, it would be something like a rep.
That means that there's a not displayed connection here from X to itself.
No, there is no. In this case, no. But to the earlier point, I think you can call this some kind of a reflexive notation at least, right? Like, yeah. Now, well, we talk about graphs, right? And causality does graphs all the time. But when we are on computers, we don't use graphs. We might use graphs to visualize things, but we typically use matrices and these kind of things, right? So very importantly, and this is often left out, I think, in many of the causality lectures that exist out there, that, you know, we should consider these other representations and discuss them at the beginning already, right? So for example, matrix representation, right? Any graph, right? Directed graph now for the matter, yeah. So where we have asymmetry between the pairs. It's just a set V and E, right? As we have seen before, over D nodes. So the size of V is D. And now we can just represent this, you know, in a different way by having a matrix, which is D times D. And that takes values 0 and 1. 0 indicating there is no edge between a certain pair, and 1 is indicating there is an edge between a certain pair, right? And then however you specify, right, typically it means that, you know, the row causes the column, right? So the arrow goes from row to column. These are important details, right? That you have to settle. But if you do, then essentially you have this property, right? Like that any entry in the matrix, right? Any ij you look at, if it's 0, that means there is an edge in the graph, right? Again, these are just notational objects, right? Like one is algebra, essentially. The other one is kind of like, I don't even know what to call it. More set theoretic, more intuitive in a sense. And yeah, what's important though is that, you know, these different representations reveal different properties, right? And, you know, if you have some results here and results there and you can bridge them, that's awesome, right? Because you can improve both fields simultaneously. Yeah? And for example, one very nice property of the adjacency matrix representation of a graph, right? We call this adjacencies, is the following, that if you take the exponential now of a matrix, you know, the regular exponential operation, right? Like you do the matrix multiplications k times, that this actually counts the paths, you know? So if you have, you know, I say a to the power of 3, then it actually counts like in the values now, all the paths of a length 3 in this case that go from one node to another. That's a very, very cool property. Oh yeah, and yeah, this is also just driving back home the fact that, you know, algebra has some nice tricks and, you know, things, and that's what we can use. And there's this comic, right? So I think that the funny thing here also is, right, obviously it shows you the meaning of what this matrix really does, right? But it's funny because it just writes it in this other way, right? But yeah, that's really the quintessence, I think. Oops, sorry. Now, if you remember from last lecture, Dave was talking about the gifts of the gods, and he was saying that Pearl said it. I was telling him he probably said it, and you know, there's these special structures, right? Why are they special? We are going to see in a moment. We're going to justify that, but just bear with me. So it's these 3 triplets, right? And they can be in any graph. They can appear any directed graph. They can be substructures. They can occur multiple times. They can be interconnected and so on, right? But essentially, it's always triplets, right? And it's either a chain. For example, you know, you go from X to Z to Y, or the other way around. It could be a fork, right? So that, you know, the middle node here, Z, is just pointing outwards, right? Or it could be this immorality we talked about, right? Like parents which are divorced, right? That essentially, you know, you have this inverted fork. You just point into a node. You sink into a node. Yeah. These are the 3 special structures. And why are they specials?
But they are not parents, they are divorced.
Huh?
They are just parents. You don't know whether they were ever
Married? Oh yeah, sure.
Yeah.
That's true. He caught me.
That's why they call it tomorrow.
Because
They should have,
oh, okay.
but we don't know.
Okay. Yeah. Interesting.
Today, we tell it every time. No, I am super happy with mine.
Okay. So yeah. Now we are doing the bridge, right? I was talking about bridges now, and now we are going to bridge to section 2. So how can graphs actually encode independence? If you had PGM, you'll notice this is the well-celebrated deseparation. Yeah. I try to just give the, I guess, most intuitive and most direct account, right? There's, you know, many treatises, you know, in different books, and they all do it slightly differently. They're all equivalent, right? But I chose this one, which is actually the one Pearl used in his book. I liked it the most. So a path P, right? A path is just, you know, if you have our directed graph and we go just through, you know, a set of nodes, is said to be deseparate, right? That's what we call it. By a set of nodes, right? So deseparate by a set of nodes. So for example, path from X to Y is going to be separated by some node Z if the following conditions hold, right? So either, you know, P contains a chain or a fork, right? So it's one of these special structures, right? It goes in one direction, or, you know, it diverges in directions, such that the middle node M, right, is in Z, right? And this is just simple to check, right? Like, you don't have to understand the intuition for the moment. I'll give you an intuition idea just now. But really, it's just a property you check. You look at a path, yeah? You look at whether it contains a chain or fork, and if a middle node is in there, right? And if this is satisfied, they're already separate, right? And the other condition is collider, right? So there's chain and fork, and then there's collider. And collider the middle node is not in Z, right? It's the exact opposite, right? But also no descendant of this middle node should be in Z, right? And that's really what you need for a path to be deseparated by a set of nodes, right? And now, we want to look at all the possible paths, right? And so we say a set is completely deseparating X from Y if and only if it blocks all the paths, if that Z is able to block all the paths, right? So really, it's just about somehow how information flows in the graph. And that's why you see now the connection with statistical independence, right? That we talked about independence. Again, remember, it's just if I have my PA given B, right? It's the same as PA. My B doesn't give me any additional value for knowing something about A, right? And this is here the same thing now with the graph that we say we have information flow between A and B, for instance, right? And if I know a certain Z, then that information is not getting through, right? Like that's the intuition. And we're going to explore this a bit more here now. So now the slide as before, but now we are highlighting also the separation. And as you can see, this is purposefully. Like this is the same notation we used in statistical independence, just now with a subscript G indicating that's for that specific graph now. And you'll see in a moment why this is, because we're going to make a full connection, yeah? But for example, if X is independent of Y, X is deseparated by Y from Y through Z in a chain graph, yeah, then we have these two situations, right? So it is independent in this case, in the lower case, where blue now means I know this variable, right? So Z is in here in this set actually. I observe Z, but they are not independent. So they are dependent in this case where we don't observe Z. And so, yeah.
Exactly.
What exactly?
The stuff that in the first case they're dependent.
Oh, sorry, not dependent. I'm talking about deseparation. Sorry. Or was this what you're pointing at? Because I'm talking about deseparation. I'm not talking about independence now. Sorry. We will get there in a second.
You will get the same question.
Okay. But yeah, you essentially see, right? So if this is the empty set, right, then this is a chain. We go back to our rule. We look at the middle node. The middle node is Z. Is Z in the empty set? No. So they are deseparated. This is all the possible paths. So X and Y are deseparated, right? And then here in this case, for this one, right? And in the upper one, it's not the case. Now, for the fork, it's the same story, right? So as soon as you observe the middle node, right, information is essentially blocked, right? Like it cannot flow. Like even though the arrow is pointing the other direction, you could actually ignore it. And you can remember this. There's also this famous baseball algorithm and these things, right? Like to illustrate this. But yeah, it could essentially flow. But as soon as this thing it's like a stone, it blocks it. You cannot go there. Huh? But for the collider, and that's why these things are special structures. It's different, right? And it connects to deseparated. It's different because only when you observe Z, information can flow and they become dependent, right? And we are going to illustrate this on an example. So these are the phenomenon we know as explaining away and these kind of things. So here, remember our graph from before, which we just exploited for notation. Now we make it an example. Yeah. So X is the random variable denoting diet, right? Oh, and by the way, I just said random variable. So we just talked about variables, right? But what we are doing here is we are using random variables as variables. And so we, can make these connections to independence in a moment. But yeah, so X is, the random variable for diet. Y is, for example, physical activity. Z could be obesity. W could be the risk of heart disease. This is all for an individual, right? So any tuple X, Y, Z, W would be a certain individual, right? Or actually a class of individuals, right? Like which all share the same properties according to this. And now the independencies, which we did.
Some earlier question, but not the other one is still on my stack. But
yeah,
I mean, saying you have a random variable that is the risk of a heart disease. Is that, I mean, now really, is that second order? Because the risk is already driven from a probability.
Yeah.
So, I mean, it's fine, it doesn't matter, but it's super interesting.
That's
Here, heart disease. I
mean, you can, of course.
I
I think the classical example would just be heart disease, right? I just put it here because I felt it wasn't. But I agree with you. On a foundational level, yes, because if we say risk is also already defined as a random variable, then it's, as you say, it's somewhat second order.
And
What-
all these models do not capture it. That's all I wanted
It's
to
a
say.
transfer. It's actually just a random variable, but it's different than the others because it's a transformation of another random variable, which is more basic, right? Like
But
the
it's
hard.
not represented. And we should
No.
maybe also think about more complex graphs where you can code these type of information as well, and go back to your
Yeah,
description of
yeah.
everyone its own child.
Yeah,
So
that's
again,
actually
make
interesting. Yeah.
assumptions wherever you use any of
Yeah. Yeah. So this is how research goes, right? Like Christian throws the ball and I play it back, yeah? And I agree with him. So what he's really just saying is that, you know, I was just telling you that these so now we're not doing lecture, now we're doing research. So
lecturing is research.
well, now I'm justified to do what I do. So X, Y, Z, and W, right? We were just saying variables. Now I told you they could be random variables, and then we can do these connections to independence. And now Christian was saying, well, but risk of heart disease, that's a very complex variable, right? So you could maybe split it up in the graph, right? But what you can also do is maybe introduce a new type of node. And we could visually depict it maybe as a square or something. And this then indicates that it's a function of some other, maybe even unknown node, right? And yeah, very interesting questions. Yeah. And now Christian is thinking, so I'll keep going. But yeah, the independencies we are denoting by the set I of G. So G is the graph we use, and then, you know, it implies some independencies. In this case, independencies, we already call them like that. This is just the d-separation statements, right? So for example, we see that, you know, X is d-separated by W given Z, right? So, you know, if I know Z, then Z contains all the information about X. So I don't need it anymore to predict W. So they are d-separated. Y, the same for W, right? It's the same structure as you see, right? And again, it's a structural property, not a parameterization property. And here X is d-separated of Y just generally, right? Because this is a collider. And yeah. Now to what I just mentioned with, you know, explaining away and these kind of things, right? Like the collider. So why is it there the other way around? That only if I know Z, for example, or W, that I can conclude something between X and Y. Well, for example, knowing that someone has a good diet X, yeah, but they are obese, yeah, which is the conclusion Z, yeah, can conclude that they are like, well, according to this graph, as long as this graph is correct, right, that they actually lack physical activity, right? Because, well, you wouldn't be obese otherwise, right? According to this graph. So that's kind of the example here. Now we want to do what we have done implicitly a bit all the time now, which is, you know, relating the actual graphs and the distributions, right? So they are two separate objects at first. However, the independent statements we can relate, right? So we see also the similar notation, right? So the d-separation statements IG, and now the independencies, the actual conditional independencies of a probability distribution P can relate, right? And for example, there's this, you know, definition of an IMAP, you know, you can also call it Markov property and so on, which is just saying that, you know, these independent statements here are just a subset of these other statements, right? So these sets that they relate, right? But you're seeing that it could be equal, but it could also be a strict subset, right? And these are the interesting cases that we are then going to look at now. So, for example, what is a Bayesian network, right? Again, there's also different, definitions for this, and I think over time it has also changed. But I think most commonly what people nowadays do is they just consider it to be a pair, right? To be a pair, this calligraphic B, which is just this tuple, you know, G and P, a graph and a probability distribution, where G is an IMAP, so all the d-separation statements are a subset of the independent statements, but with the additional property where if you remove an edge from G, this would also remove this property, right? Like it's somehow the minimal IMAP, we call this usually, right? You can always add edges because that will not introduce, you know, new independencies, but you cannot remove. And now also, because again, we are talking about graphs, a Bayesian network is a directed acyclic graph, right? So we talked about directed graphs, but here we briefly had the interaction with cycles and these things. Typically in causality, we have these acyclic structures. Dave mentioned that recent work has looked at cyclic and so on and so forth. It's very difficult, but this is typically the case. Why? Because, well, we looked at these Bayesian networks and these things, and this ends up happening, right? And you can actually prove a lot of amazing things with this. And so obviously this explains also the success. Also, you know, Bayesian networks, you know, inference and these things, that it's a very organized way of structuring. It's not a computation graph in that sense. It's a semantic graph. And so, yeah. And yeah, just shortly, so what does it mean? Well, all edges that you see, they are all directed, right? Like they have to decide either I point in this direction or the other. And there's no directed path, which is a cycle, which means, you know, no self cycles, but also no A goes to B, goes back to B, or A goes to B, C, and then goes back to A, or something like this. Yeah. Now, I'm going to jump back a little bit. So this is more recent research, actually, and I think this has never been discussed in any of, you know, introductory lectures, and especially not basics, but I think it's important. I told you how, you know, there's graphs, and then there's matrices that represent graphs, right? And there's nice properties, like, for example, the exponential, which counts, you know, the walks, the paths. Then actually, we can formalize a so-called cyclicity constraint, right? It's this following analytical characterization where this is the matrix exponential, right? So it's not just, you know, like, well, there's a specific formula, right? E to the power of A and what that means, right? It's different from A, you know, to the power of K. And TR is just a trace operator, right? Like taking the sum of over the diagonal, yeah? And here the circle thing is just multiplication. You're just stacking two matrices, right? Like you take the first from first, multiply second, and so on. The Hadamard product, we call it. And if this thing is 0, then you are acyclic. Yeah, that's very cool, because essentially this matrix exponential can quantify whether and how many cycles you found along any, because this is it's a series essentially. This is infinite, right? It will check for all possible. That's why we also approximate it. You can check for all possible lengths of paths, whether there's a cycle or not, essentially, right? And then if you characterize like this, it'll put it all on the diagonal. You take it minus the dimensionality, and that's only 0 if it's actually a cyclic. And that's actually very useful if you're then trying to learn these graphs in the first place, right? And you're interested in learning DAGs because, well, cyclic relations are a pain in the ass.
Well, that's only useful if you want to be learning in a continuous session.
Yes.
You can also learn in a combinatorial. You don't need to.
But then it explodes, right? Well, this is,
But that one explodes as well.
yeah.
Well,
What do you mean?
You have to approximate the exponential.
Sure, but you can cut off smartly, right? And it works a lot better, right? That was the whole point of their paper, yeah?
So then you approximate in a smart way. You can approximate
Yeah.
the combinatorial way also in a smart way.
Yeah, I don't know. We have to discuss this. I agree with what you're saying, but yeah.
Big question, let's take it off.
Yes. See, I still have to learn these phrases. Yeah, I'm not there yet. But yeah, so this actually what Christian just mentioned, right? So working with DAGs is hard because of this exponential explosion of this combinatorial growth. And I want to illustrate this, yeah. Oh man, I should have kept this number away and asked the audience. See, I'm not smart. But yeah, you see the answer now. 4 nodes, right? Like just as our diet, obesity, heart disease, and physical activity, right? There is 543 different ways I can put edges between these things, yeah, and not edges for that matter, right? And of course, which direction it points, but without cycles. It's not even counting the cyclic models, right? Like 543, 4 variables. What the fuck? I don't get this, yeah. And this, so I showed this also to Moritz, right? Like we always laugh about this. This is a very nice way of showing this. So here you see on this axis, in the first column you see the number of variables. So you see 4, and then number of DAGs with these nodes for 543. And now for 5 variables, you just add 1 more variable. It's almost 30,000. I mean, what? And then you actually go here, and actually the length of this number increases faster than any linear term. Yeah, this is a very nerdy and geeky thing to, you know, celebrate, but I think it's crazy. I do, and it's ridiculous.
Yeah, but even better, you see why scientists will always have a job.
Why?
Too many questions.
Yeah, well, sure.
You have to find the graph, too many of them.
This is ridiculous, really. And yeah, so now briefly, so we just talked about, you know, graphs, matrices, the d-separation, that we can relate it somehow to independencies. And now I want to talk about some important properties, right? actually, it's really just one property expressed in different ways. They are equal, but they are different properties. They are an end effect equal, essentially, right? So I try to summarize this nicely for you because, you know, some books will just introduce one and some the other, and then you're like, what the heck, what's going on, right? So they are the Markov properties. And I guess this is really like Kolmogorov called after this guy Markov, I guess, just like the hidden Markov models and so on. I'm not sure. But yeah, given some DAC G, the global Markov property is really just this property of IMAP, which we saw earlier. So if we have disjoint sets A, B, and C, then for any choice of those disjoint sets, right, it's just a partition, we have that the D-separation implies the independence, the conditional independence, right? So essentially, it's just subset equal, right? That's what it's saying. Like it could be everything, right? But it's definitely at least not more, yeah. And then there's something which and it's global because, well, you see, it's like kind of on the whole graph, right? Like any kind of D-separation. Now we move to the local Markov property, which is local because we are looking at variables and their neighborhoods. And what we have here is this non-descendant sets, right? So we have that for all variables, they are statistically independent of their non-descendants given their parents. Essentially, they shield off all the information, right? Like there's also other terms like, you know, causal kernels, Markov kernels, whatever. And then finally, there's the factorization, right? Which is just, you know, this Bayesian network structure, right? For example, here we see that, you know, PV is again all the nodes of the graph, right? And then that you have this equality. It's just this big product. It's just this decomposition into all of these modules where, you know, you have these variable xi given its parents, right? And here, for at least for these two, you can kind of see that they should be very similar. For this one, it's a bit different, but eventually you can prove, right? There was this work by Lauritzen, I think, from Copenhagen, like 30 years ago or so, which really just showed that, you know, if P has density, this doesn't mean continuous, right? Like discrete probability mass function, you can also see as a density, as long as it's essentially like the regular case you look at and not some, you know, Cantor distributions or whatever, then they are all equivalent, yeah? And this is really, really nice, yeah?
So one comment, and now first to understand factorization means according to the graph.
Yes, correct.
I mean,
correct,
it's good.
correct. Correct. That's
Right. So now, isn't it the downside that we don't have equivalence up there, but an implication? Because I'm now very nervous, right? I don't want to make the wrong assumption. And because I only care about INET, I will always go for the fully connected Bayesian network to not take out anything. And that means in the end, I'm learning a neural network because I don't care about insights, just to be careful enough to not make an independency assumption that is wrong, and by that in turn doing a causality statement maybe that is
So
causality.
I agree. We have to be careful. Then again, even then we can screw up, right? But what you are pointing at now, so also for everyone else to join this discussion, or at least, you know what we're talking about. So
but really up there, right?
Yeah, exactly.
Saying I have the graph, and then
because if you take a fully connected or so-called complete graph, that is an IMAP, so it satisfies this for any distribution actually. This you can show, but essentially it just tells you because there's no the independent set is an empty set, and the empty set is a part of every set. So it's always satisfied, right? But for the Bayesian network, I told you about the minimality thing, right? So you discard those complete graphs, and there is ways. I mean, I remember also, and I would have to check, but for example, in Koller and Friedman's book, right? They also show a construction of a minimal BN as long as you have some ordering. I don't know how much you have to assume now on the ordering, but if you have like a causal ordering.
When is it an equivalence?
Oh, you mean whether when here's the equivalence?
No, I would love to have. What is the chance to have an equivalence?
I mean, to have here equivalence is just the faithfulness, right? Which is the parameterization thing, which is
you should not talk to me.
also. Yeah, but this is coming in a second. Yeah. Yeah. Then we'll just jump further. Yeah, it'll come in a second. So but yeah, before we do that, just one more example again. So as you can see, I'm using this as a running example to make it familiar. But you know, we again have our A, B, X, and Y from before, right? With the 200 samples now in this case. and we said that X and Y here are uncorrelated, but they are marginally dependent. And here's a different perspective now to see this with the graph, which is really cool. The implied graph by these equations, right, is the following. You have A and B, yeah, they are the noise variables, right? And then A cause X and Y, and B cause X and Y, right? And this separation will tell you, for example, these two things now. It does cause. I just haven't introduced causation yet, yeah.
That's why you should say
But it, yes, cause, but it does, yeah. Believe me on this, yeah. But he's right, yeah. I haven't introduced it though. Oh man, yeah. And
Moritz, can you make a note? That's really good. It's like we can have a t-shirt.
it's causation, believe me, yeah.
You will love it.
Oh man, yeah, he will actually love it, yeah. Yeah, and then so this separation just tells you, right, if they're dependent, so they are deconnected, yeah.
They're just saying they're not de-separate.
Yes, correct. They're not de-separate, they're
Saying that
deconnected.
dependent. That's exactly the point.
Yeah, but we are doing this connection now. Yeah. Okay. Yeah, but I agree. Yeah. And then here, X, Y are separated, given A and B, right? And so again, also if we make our example from before, right, like where we had with the collider, and we said, if I observed that you are what was it, that you are obese and that you also have diet, yeah, a good diet, that must mean that you have a bad physical activity going on. And here you can see, right, like if I know, for example, A or B, well, A is, according to these equations, responsible for computing X and Y. I'm not using the word cause. And and so, if I know A, well, it contains the information to compute both of those, right? So it kind of gives you the insight that, information can flow. And so this is now the graphical perspective. Okay, so now here, see the slide, Christian, here, equivalence. So equivalence of deseparation and conditional independence, we only have, right, so IG equal IP, if the distribution is what we call faithful, yeah? That really just tells you there's no independence that is not implied by the graph structure, right? Like the set, so essentially it's the other way around, that if you have any conditional independence, it implies that it's in the graph, right? It's a subset of those, right? And it's not more, yeah? And can be violated, and this is big thing because it's not a structural property, right? And that's probably the fundamental divide, right? And that's the problems that Christian was just talking about. It's a thing of parameterization. For example, if we have these following three equations, X, Y, and Z, yeah? We take those Ni again to be some noise variables, and we say they're normally distributed. So X is just its noise, Y is some A times that Nx plus Ny, and then Z is just By plus Tx plus Nz. Then the implied graph structure is the following, right? So you see that X is what we will later call a common cause or confounder of Z and Y, and Z is pointing to Y. And now if you have the following condition, right? It's not important how you derive it now, like who came up with this and where it comes from, right? It's just important to note now, you can, check this for yourself, but essentially what it gives you is that X is marginally independent of Z, which is of course not implied by the graph, right? Like there's an edge literally pointing between X and Z, yeah? But yeah,
I think it's easy to understand, because essentially what you're coding is, you say I give the illusion that there's no independency.
Yes.
But now I'm coding the independency into the parameters, and that's the root you're putting there, right? So everything into its zero, so you say it's the root. And then it's also interesting to see, because you can now ask how many roots are there, and actually there are finitely many of them. And so what is interesting is that, the probability that two randomly generated distributions will actually show an independency, though there is no independency on the graph structure, is neglectable.
Yes.
And that's the nice part.
And that's this.
Oh, sorry.
Yes. And that's this. No, Christian is too smart for us, yeah?
No, I never.
Yeah, me too. Just a second, I'll just bring back this one point. So essentially, really, for almost all distributions P, right? This is a general statement, right? Like whatever it is,
That's factorized over G though, right? This is the condition. And again, factorized over G, it's this, IMAP property, this local Markov property, that except for a set of measure zero, and this is the thing, it's finitely many, and any singleton is measure zero, and a finite collect, not even an infinite collection, but countably infinite collection of these measure zeros is still measure zero. So essentially what it really tells you in the intuition is that, a slight wiggle should, get rid of these extra independencies, yeah? Because essentially what Christian was saying here, this is you are kind of encoding this illusion. You are putting the parameters in certain ways such that you cancel out paths, right? Like as if they were not in the graph. And then of course, you don't have the independence. But yeah, this, I wanted also to end this on a positive note, right? Because this is kind of reassuring, right? And so this is really the end. We're going to take the question in a second and all other questions. But I like this comic as well, right? That, we were talking about dependencies, right? And sometimes it's just the little things, yeah? There's like the whole modern infrastructure, but there's this little thing, and it's a project by some random person in Nebraska, thanklessly maintaining this since 2003, yeah? So actually, Moritz, you were giving an example for this, right? Like, was it curl, right? From Linux.
Maybe.
Yeah, I think Moritz was telling me like we have to check, but like that, for example, this curl, package software, whatever, right? Until like just recently was maintained by a guy for like exactly like this, like for like 30 years or I don't know how long, and yeah, thanklessly. Or for example, if you have Windows, the WinRAR, to extract your archives, right? Like no one pays for that, right? But it's amazing, yeah. So yeah. Okay, you had a question up there, so.
Shouldn't the edge from Z to Y be the other way around?
Shouldn't the edge from Z to Y be other way around? So you're saying that Y should be a parent of Z? Oh, yeah. Sorry, a typo. I'll correct this for the slides. Thank you. Because you see, Z is computed as an argument. So yeah, of course.
So I think it's really beautiful. This last result is essentially showing that we just need graphs, except for all the other modeling questions. And this is why you will see Judah Pearl jumping up and down and telling everyone graph, and things of graphs. And it's amazing. And you should try it out. Go to your fellow and don't talk about probabilities. And then you do the random experiment and you one day talk about graphs. You will see that most people like much more to talk about graphs than about probabilities. And that's the amazing part. And then going one step ahead, you will see a lot in the class here and also in PGM, but here much more is that then actually you can use graph theory for many questions in probabilities in things that have to be quantified, all of a sudden just become a question of graph theory, and that is so beautiful.
Yeah,
and it's like when you said the other way around, oh, here's a combinatorial problem, but we put it into the continuous part.
And now we can use tools from continuous, which have worked well to, improve things in graph.
It's so fantastic because it means maybe in our brain, something like that happens, because you should all ask yourself, okay, if causality is also combinatorial, how do we do that in our brains? Because this is maybe not combinatorial, but it's combinatorial. So this is where currently there's so much going on in science and really deep questions. And it's really beautiful.
Yeah. Yes, it's amazing. You should come and do a master thesis with us if you are still free. Yeah.
And PhD.
And PhD. And poster.
And
Yeah, true. Yeah. So.
And company. We are happy to go for.
Oh yeah, we also do companies. Yes. No. Yeah. Any other questions, thoughts, impressions? Right. So these were the basics, right? So probabilities, why we use them, what are they? Independence, what does it mean? Correlation, what's the relation between those? Graphs, how do we represent graphs in computers? What's the relation to independence? All of these three things. Yeah.
When we introduced the Bayesian network, we defined it, the Bayesian network with the square is the minimal time of the probability. Was it called when it's not minimal?
What do you mean exactly? When is that?
So
you mean if I have the same structure, I just have graph and distribution, but it's not a minimal IMAP?
yeah,
it's not a Bayesian network.
Yeah, but that's correct. Practically no one cares. It's not like you're sitting there, you draw your
Yeah,
graph, and you
sure,
say,
sure.
okay, now I first have to find
Sure,
my set of
sure.
distributions where this is minimal above. No,
Sure.
but if you really want to understand whether what we are doing here is modeling the real world, then you should do. But of course, at some point, you just write you drop and you say, okay, I'm modeling my graph, and I know I can always find a situation where everything is good.
So maybe also to add to Christian's points and where your question might be hinting at, right? Like if we look at, again, the practical stuff, right? And you have some data distribution or data, and you learn even this distribution, right? And you have some expert who tells you this should be the graph or somewhat the graph, I'm even not sure, right? Then obviously you could not prove this, right? It would be difficult, but it would be weird to not call it the Bayesian network. So I guess formally what we would then do is just say, well, I assume my expert is good and my model has learned the distribution well. So this is a Bayesian network.
Well, it goes also deeper into the question of subjective probabilities and objective or probabilities. So the one is it a true probability independent of myself? And the other one is, can I imagine a situation where that is the true Bayesian network? And I think most of the cases we are in this subjective situation, but it goes deep, this discussion now. I guess we can have a whole class on the philosophical implication, and I mean, is what we observe the real world? What is the real world? Can we at all simulate the real world? I mean, so I just want to, if you're confused, it's good because it's very deep.
Yes.
Well,
in PGM, I take the pragmatic part and say, yes, indeed. And then in the follow-up, we talk about the representation theory. And I go the way of telling you, if you have this graph, you can find a distribution that agrees with the graph. So it's equivalent, but it's the more pragmatic approach.
And then again, also just to this deeply philosophical thing, right? Like, that's so true, right? But we should not think in boxes, right? Like you were assuming, no, okay, PGM, right? No, maybe not assuming, right? But you were just questioning, why are they different, right? If we call them the same thing, right? But then again, what is right or wrong? Is there independent objective truth, right? Like last lecture, right? Like we were motivated causality, right? I also told you that this lecture is a bit special also in the causality context because we're trying to give the broader picture, show not just Pearl, but also, Imbence's framework, Neyman Rubin, right? Potential outcomes, Granger, I don't know, Halpern and actual causation, right? Woodward, whoever, right? Like this, it's so big, right? We just have a certain definition of causality, and that's why we present it formally, so we can actually, concretize it, right? But other than that, whether we have the right formalism or not, we were just justifying last time, well, it's the most successful so far because it's closest, I guess, to the way machine learning works. And so we could already transfer some, things and make things work, right? But doesn't mean that it's the ultimate truth or whatever, right? So deeply philosophical, very fun questions. I love these questions. Yeah.
Speaking about modeling the real world, it seems there would be many cases where we would need a cyclic graph or maybe Markov chain to
You like cycles, no?
to describe what really happens.
So this is an ongoing cutting-edge research question, right? Stefan Bongas, Joris Moy-Peters, Patrick Fauré, they had this work. 6-7 years they were studying this. They finally published it. Foundations of cyclic structural causal models and these things. And even there, I mean, mathematically, I think super sound, amazing, great achievement. But like on a practical level or so, still has not really much, right? So what it's really telling you is that there is it's difficult, right? Like you relate it to other philosophical topics on logic, right? Foundations of logic, Gödel and something. How much can we know about truth, right? What can we even prove, right? So think of, for example, the famous conference here for causal learning and reasoning, CLEAR. It's in the 3rd edition now. Actually, just tonight I had a deadline for this. And they have the chicken and egg problem, right? Like what came before, the chicken or egg, right? Like you can go back and then at some point there was something which was an egg, but it was not really the chicken egg. And that's the origin, right? But now you can go even further, right? And go beyond. And cyclic ones are.
But you can always translate.
Did you write all of this down in so
Yeah.
short?
But this is just because the third slide was a bit boring. So I inserted now. No, but here is one way to translate if you want to have cycles. So maybe you can check. I mean, there are Markov networks that look at least undirected, and they don't make an assumption on the direction. But what you could do to simulate something like that with directions is that you have your two random variables and you say there is this constraint that I'm putting in there. And I'm always saying this is true, but I never observe it. I mean, I always observe it. I make this assumption because what is happening is you're putting a conditional distribution table now there, right? So you have here C and then you have here X and Y. But because you always assume C is true, essentially you're cutting away half of the table, right? You're taking only the one where P is always true. And the zeros you don't care. So essentially you don't care about the direction, you only give here costs on how much does it violate if X and Y are in particular configuration. And that's exactly like what you do if you have an undirected. Because in an undirected case, you're not saying the one is the reason and the other is the reason, but you're just saying if the two are in this configuration, then I have to pay that price. And so you can always, at least in the finite case, map from an undirected to a directed. In a sense, also from a directed to an undirected one, because that's what we do anyhow to compute probabilities. So if you allow yourself extra variables, and Judah would always tell you, I'm not happy to spend extra variables because I have to make additional. But per se, don't worry. You could go for an undirected relationship already with directed.
Another way Judah would also put it is he always says, I don't understand 5 variables, let alone 1,000. So if he has more variables, then he's close to 5. So yeah. Anything else? I think we are already on time as well. Slightly over, but to start with the If not, then yeah, same place, same time next week. And then we are going to talk about causal hierarchy. We start with causation. Yeah. Thanks again.